Today, we shall study about Bohr model of hydrogen atom in the chapter Atoms. Bohr combined classical and quantum concepts and gave his theory in the form of three postulates. Bohr's first postulate was that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy. Contrary to the predictions of electromagnetic theory, according to this postulate, each atom has certain definite stable states in which it can exist. And each possible state has definite total energy. These are called the stationary states of the atom. Second, Bohr's second postulate defines these stable orbits. This postulate states that the electron revolves around the nucleus only in those orbits, for which the angular momentum is some integral multiple of h by 2 pi, where h is the Planck's constant, 6.6 × 10 to the power minus 34 joules second. Thus, the angular momentum L of the orbiting electron is quantized. That is, L बराबर nh by 2 pi. Now, Bohr's third postulate incorporated into atomic theory the early quantum concepts that had been developed by Planck and Einstein. It states that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted having energy equal to the energy difference between the initial and final states. The frequency of the emitted photon is then given by h nu बराबर EI minus EF, where EI and EF are the energies of the initial and final states, and EI is greater than EF. For a hydrogen atom, equation E बराबर minus E square बटा 8 pi epsilon naught R gives the expression to determine the energies of different energy states, but then this equation requires the radius r of the electron orbit. To calculate r, Bohr's second postulate about the angular momentum of the electron, the quantization condition is used. The angular momentum L is given by L बराबर mvr. Bohr's second postulate of quantization says that the allowed values of angular momentum are integral multiples of h by 2 pi. इसलिए Ln बराबर mvn Rn बराबर nh बटा 2 pi, where n is an integer, Rn the radius of nth possible orbit, and Vn is the speed of moving electron in the nth orbit. The allowed orbits are numbered 1, 2, 3 dash dash according to the values of n, which is called the principal quantum number of the orbit. From equation third, Vn बराबर E बटा रूट ओवर E बटा रूट ओवर 4 pi epsilon naught mRn. Now combining it with equation third, we get the following expression for Vn and Rn. We get Vn बराबर 1 बटा n into E square बटा 4 pi epsilon naught 1 बटा h बटा 2 pi, and Rn बराबर n square बटा m into h बटा 2 pi का whole square into 4 pi epsilon naught बटा E square. The size of the innermost orbit n बराबर 1 can be obtained so as R1 बराबर h square epsilon naught बटा pi me square. This is called the Bohr's radius, represented by a symbol A naught. Thus A naught बराबर h square epsilon naught बटा pi me square. Substituting the values of h, m, epsilon naught and E gives epsilon naught 5 बराबर 5.29 × 10 to the power minus 11 meter. From equation we see that the radius of the orbits increase as n square. The total energy of the electron in the stationary states of the hydrogen atom can be obtained by substituting the value of orbital radius as En बराबर माइनस ई स्क्वायर बटा 8 पाई एप्सिलॉन नॉट m बटा n स्क्वायर इंटू 2 पाई बटा h का होल स्क्वायर इंटू ई स्क्वायर बटा 4 पाई एप्सिलॉन नॉट और En बराबर माइनस me4 बटा 8n स्क्वायर एप्सिलॉन नॉट स्क्वायर h स्क्वायर सब्स्टिट्यूटिंग वैल्यूज वी गेट En बराबर माइनस 2.18 now 10 to the power minus 18 joule बटा n स्क्वायर joule. Atomic energy are often expressed in electron volts rather than joules, since 1 electron volt बराबर 1.6 गुना 10 पर माइनस 19 जूल, इसलिए E बराबर माइनस 13.6 बटा n स्क्वायर इलेक्ट्रॉन वोल्ट. The negative sign of the total energy of an electron moving in an orbit means that the electron is bound with the nucleus. Energy will thus be required to remove the electron from the hydrogen atom to a distance infinitely far away from its nucleus or proton in hydrogen atom. If we assume that the electronic orbits are circular, though orbits under inverse square force are in general elliptical, planets move in elliptical orbits under the inverse square gravitational force of the gravitational force of the sun. However, it was shown by German physicist Arnold Sommerfeld that when the restriction of circular orbit is relaxed, these equations continue to hold even for elliptical orbits. One electron wave function called the orbital, this function depends only on the conditions of the electron. Thus, we have two differences between two models. Bohr model is valid for only one electron atoms, and energy value assigned to each orbit depends on the principal quantum number in this model. We know that energy associated with a stationary state of an electron depends on n only for one electron atoms or ions. For a multi-electron, this is not true. The solution of the Schrödinger wave equation obtained for hydrogen atom, like atom or ion, called the wave function, gives information about the probability of finding an electron in various regions around the nucleus. This orbital has no resemblance whatever with the orbit defined for an electron in the Bohr model. Now, energy levels. The energy of an atom is least negative value when its electron is revolving in an orbit closest to the nucleus. It means the one for each n बराबर 1, for n बराबर 2, 3 dash dash. The absolute value of energy is smaller, hence the energy is progressively larger in the outer orbits. The lowest state of the atom is called the ground state. Is that of the lowest energy, with the electron revolving in the orbit of smallest radius. The Bohr radius n0. The energy of this state n barabar 1 E1 is minus 13.6 electron volt. Therefore, the minimum energy required to free the electron from the ground state of the hydrogen atom is 13.6 electron volt. It is called the ionization energy of the hydrogen atom. This prediction of Bohr's model is in excellent agreement with the experimental value of ionization energy. At room temperature, most of the hydrogen atoms are in ground state. When a hydrogen atom receives energy by processes such as electron collisions, the atoms may acquire sufficient energy to raise the electron to higher energy states. The atom is then said to be in an excited state. From equation 8, for n बराबर 2, the energy E2 is minus 3.40 electron volt. It means that the energy required to excite an electron in hydrogen atom to its first excited state is an energy equal to E2 minus E1 बराबर minus 3.40 electron volt minus 13.6 electron volt बराबर 10.2 electron volt. Similarly, E2 बराबर minus 1.51 electron volt and E3 minus E1 बराबर 12.01 electron volt. Or to excite the hydrogen atom from its ground state, from its ground state. From its ground state n बराबर 1 to second excited state n बराबर 3, 12.09 energy is required, and so on. From these excited states, the electron can then fall back to a state of lower energy, emitting photon in the process. Thus, as the excitation of hydrogen atom, from these excited states, the electron can then fall back to a state of lower energy, emitting photon in the process. Thus, as the excitation of hydrogen atom increased, that is, as n increases, the value of minimum energy required to free the electron from the excited atom decreases. In this diagram, the highest energy state corresponds to n बराबर infinity and has an energy of 0 electron volt. This is the energy of the atom when the electron is completely required or completely removed r बराबर infinity from the nucleus and it at rest.